So this is our Kinetics project presentation, and we titled it "Characterizing Drug Degradation Rates." I'm Jaiden.
I'm Alex. Ian.
I'm Noah.
Alrighty, so let's get right into it. So overall goals for the project, we started out by our goal was determining our rate order and our observing our rate constant for the degradation of our phenolax and piactinin drugs in the NaOH dilution set. And by determining this, we can determine our shelf life. And once we did all that, we were able to, find recommendations on determining conditions to help extend our shelf lives.
All right, so as Group A, our first approach was use the 300-second interval of the spectrometer, and our original dilution set was 40 microliters of phenolax and 3 milliliters of NaOH. But that set didn't really work since we had a very low starting absorbance, which was 0.6 when our absorbance was supposed to be closer to 1. So we had to up it by 5 microliters of phenolax and keep the 3 milliliters of NaOH. And so we input our raw data after running the spectrometer into Excel, and we use various math functions like just phenolax versus time, log natural phenolax versus time, and 1 over phenolax of time. And the results show that the reaction was a first order reaction because the log natural phenolax versus time had the highest R squared and was pretty linear. And so using those graphs, we got that the reaction was first order again, and we had to use the first order equation of negative log natural of 0.9 divided by our K absorbance value in order to find the T90 value. K absorbance is just negative slope of the graph that we chose, which was the log natural phenolax graph. And we found that that slope was negative 0.0107. So we just plug that in to the negative slope that moves it over to 1.07 times 10 to the negative 2. And so we plugged that into the log natural 0.9 over K absorbance value, and we found that the T90 value was 9.85 seconds.
All right, for Group B, our experimental approach was very similar to Group A. Our dilution set consisted of 7.5 milliliters of NaOH and 2.5 milliliters of nanopure water. Of that, we used 3 milliliters in our mixture. The volume of phenolax we used in this mixture was 35 microliters, totaling the mixture to 3.35 milliliters. The spectrometer readings, after we pipetted the mixture out and put it into the spectrometer, gave us the following data on N, K observed, and T90. Our reaction data was input into Excel. We first got the concentration of phenolax and set that against time. We then got the log natural of that phenolax equation and set that against time, and then we got the 1 over the phenolax and set that against time. Of these three, the R squared was the highest on the log natural of phenolax, meaning the reaction is first order.
So for our piactinin testing, we diluted 3 milliliters of NaOH with 12 milliliters of water. This was different from our phenolax experiment because we did not dilute NaOH there at all. We used 100 microliters of piactinin. Otherwise, our procedure was the same. So a quick summary, after finding our spectrometer data, we input it into Excel. We found the concentration by using Beer's law, and then we used the Excel software to get the 3 graphs we have below. Since the R squared was highest for the natural log graph, just like for phenolax, we know that the reaction is first order. Then we used the slope, took the negative of that, got the K observed value of 0.0115. We plugged that into the equation and we got a T90 shelf life of 9.161 seconds.
All right, to be more accurate with our results, our group also tested the piactinin, but ours actually had 3 different solutions based on our starting absorbance. So with our first solution, we had the 3 milliliters of dilution with the 2.5 milliliters of NaOH, the 7.5 milliliters of nanopure H2O, and we also had the 75 microliters of the piactinin. And with this mixture, our starting absorbance was 0.4. We wanted to be close to 1. So with this number, it was too low, so we needed to make a change. So what we did was we upgraded the microliters in the p-actinins and from 75 to 90, and then we had our starting absorbance changed to 0.6. However, we still can make it closer to 1, so we did another solution where we actually lowered the milliliters of the NaOH and raised the milliliters of the nanopure H2O. And then our starting absorbance was raised to 0.8, so we felt this was more accurate in determining our charts.
From those, we got our graphs using Excel. And once again, we determined that it was first order because the log natural of pioctinin is the highest R-squared value of our graphs.
So moving on to a comparison of the results between the groups. For starters, both of the groups concluded that phenolax and pioctinin degradation is a first order reaction. When testing phenolax, group A had higher R-squared values. We assumed that this is because group B had a larger time interval, which made the points near the end of the line skew the best fit. When measuring pioctinin, however, group B had the higher R-squared values, probably because they had a shorter time interval than we did for group A. Otherwise, the experimental approaches were basically identical, except for the concentrations used. Group A had to repeat the experiment for phenolax because we had too low of a starting concentration, while Group B had the same situation, but for pioctinin. Further experimentation could be done by using differing volumes of phenolax and pioctinin to improve the results and get more accurate R-squared values and rates. Additionally, more efficient pipetting and transfer of samples would improve the reaction because it wouldn't be occurring before we get the solution into the cuvette, and that would get us a more accurate starting absorbance.
Alrighty, so to end it off, for our shelf life recommendations, the first two can go hand in hand with storing in cooler conditions and keeping away from heat. By keeping, these medicines near heat, it actually will, make the medicines more toxic and its effectiveness will decrease. So we noticed by maybe storing in cooler conditions, it will continue on its effectiveness over a longer period of time. And also noticing that some medicines, or drugs, will, do best in fridges. So it's good to pay attention to that.
Another way to improve the shelf life will be to efficiently transfer the samples. This is to mitigate the high degradation rate of specifically phenolax and pioctinin. Another solution could be we could use more alkaline solutions that are not NaOH, see if they slow the reaction down a bit. Or we could change the pH balance of the nanopure water to see if that slows down the reaction or speeds it up. And finally, we could change the final mixture from a liquid to a solid using a solidifying agent of some variety to make it an ingestible pill.
All right. This concludes our presentation. So thank you for listening in and hope you have a good rest of your day.